Hello students, welcome to the heat transfer lab. Today we are going to discuss the experiment number 9, that is 10 test on counterflow heat exchanger. Okay, so here the aim of the experiment is to study the heat transfer phenomena in counterflow heat exchanger and to determine three parameters. One is LMTD, that is logarithmic mean temperature difference. Second one is overall heat transfer coefficient, and third one is effectiveness. Okay, so heat exchanger apparatus and stopwatch and thermometers are the required for this experiment. So this experiment setup is a tube in tube heat exchanger, means the hot water flows inside the inner tube while cold water flows in an annular space between inner and outer tube. A water heater tank is provided for supplying hot water continuously, and cold water always flow from the left to right. Okay, 6 valves are provided for the controlling the direction of the flow of hot water, and 4 thermometers of trapping the provided for the measuring inlet and outlet temperatures of the hot and cold water. So here the specifications of the heat exchanger they are given. That is diameter of the inner tube 10 mm and length of the heat exchanger is 1 meter. So we have to find out three parameters, that is LMTD, that is logarithmic mean temperature difference. To calculate this LMTD, we require theta I and theta O. Okay, what is theta I? Theta I is nothing but THI minus TCI. That is hot fluid, inlet hot fluid temperature and inlet cold fluid temperature. And TO is nothing but inlet, outlet hot fluid temperature and outlet cold fluid temperature. So once if you know the theta I minus theta O, we can calculate LMTD. Okay. So the heat transfer from of one fluid to another fluid is given by the expansion. For the counterflow, we already discussed in the theory class for the derivation for the counterflow. So that is Q is equal to UA d delta T M. Okay, where delta Tm is LMTD and U is overall heat transfer coefficient and heat A is the heat transfer area. So here we have equation LMTD, that is the theta I minus theta O is equal to logarithmic of base to the E of theta minus I divided by theta O. Okay, here the line they are used is nothing but logarithmic base to the E, that you keep it in mind always. So here the counterflow heat exchanger diagram. So one is hot fluid is moving in downward right from left to right, and cold fluid is moving left to right. So that is theta I and theta O will be given in the diagram. So based on that you can take the difference of the temperature of the fluid, you get the values. And here one more equation is overall heat transfer coefficient, that is U is equal to Q divided by A delta Tm. So Q already you know that the capacity, that is specific capacity also we can say, or thermal capacity we can say. So that is MH CPH into THI minus TCI is nothing but QH, and QC is equal to MC into CPC into TCO minus TCI. So these are all the equations for finding the Q. If you know the Q, then you can find out the overall heat transfer coefficient. So that is U is equal to Q divided by A into delta Tm, where A is the area, surface area, that is pi dl, and where L is the length of the tube and D is the diameter of the tube. Next, effectiveness of the heat exchanger. For the counterflow, this is the equation, that is epsilon is equal to actual heat transfer divided by maximum possible heat transfer. So there are two conditions. If MH into CPH is less than MC into CPC, you have to use this formula, that is THI minus THO divided by THI minus TCI. Or if MC and CPC values greater than this value, that is MH into CPH, then we can use this formula, that is TCO minus TCI divided by THI minus TCI. Okay. Based on that condition, we have to use that formula and find out the values. So how we have to conduct the experiment? Here the steps are like this. First one, to close the valve V1, V2 open completely. The valves V3, V4, V5 and V6. Okay. The procedure is, first one, you close the valves V1 and V2 and open valve completely, that is V3, V4, V5 and V6, and open the delivery pipe for hot and cold water. Second one is to start the power supply to heater and insert the 4 thermometer in their holders and adjust the flow rate of so as to obtain sufficient temperature difference. Then wait until steady state and note down the thermometer readings. Once you get the thermometer readings, use some measuring flask and stopwatch to measure the flow rate of the hot water and cold water. You have some flask will be there. You have to collect the water, hot and cold water, so measure to find out the flow rate of the hot and cold water. And last one is switch off power supply and cut off the water flow. So this is the procedure, and following are some observations. There are time for 1 liter flow rate cold water and time for 1 liter of flow of hot water, and inlet and outlet temperature of the hot and cold waters and outlet. Okay, these are all things they have given. And calculation part, mass flow rate of hot water and mass flow rate of the cold water, and rate of heat lost by water and rate of heat lost by the cold water. All these things to be calculated by using these formulas and get the values. Okay, thanks for watching this video. Welcome to the heat transfer lab, students, and today we are going to conduct the experiment on counter flow heat exchanger. So already you know that how to conduct the experiment on heat exchanger for the parallel flow. Only in a single setup we can conduct the two types of experiment. One is parallel flow and counter flow. Now we are going to conducting counter flow heat exchanger. So what is my counter flow? Very basic is the counter flow you understand. If you understand the counter flow heat exchanger concept, you can easily conduct the experiment. So counter flow means at the center of this channel, the water hot fluid is moving in this direction, and the adjacent to this, the cold water is flowing. Okay, it is moving in this direction and the cold water is moving in this direction. So both are in opposite direction. That is called counter flow. Okay, here also same 6 valves are there. Only by controlling valve only we can conduct this experiment. Okay, this is the heater. We have to switch on heater and it get allowed to, and also we have to tap on to allow the water into this heater to heat it up the water. Once the water is get heated, so we are allowing to flow water in this channel. Okay, so we have to close and these all are get open. Once the hot water is flowing, fluid is enter into this channel, so again we have to open this valve. Okay, this valve, so allow this water to take the counter flow action. So here the cold water will be flowing in opposite direction. So already hot fluid is flowing in this direction. By opening this valve, these two valves, cold water is flowing in this direction and both water is flowing in opposite direction. So that is what counter flow is taking place now. So after that, so the temperature of the hot flow fluid exit and cold fluid exit will be calculated by exit temperature. By this is the exit pipe. So here we can find out the temperature of the hot and cold fluid of the exit. Okay, so this is how we are going to conduct the experiment, and these are the some formulas as you know about this counter flow heat exchanger. This is the diagram of, so you have seen now, this is the counter flow type of heat exchanger. So here theta I and theta O also we have to find out. Theta I means the temperature of the hot fluid inlet minus cold fluid inlet, and theta O means the hot fluid outlet minus temperature of the cold fluid outlet. So if you know the temperature difference of these theta I and theta O, you can calculate the LMTD. LMTD is nothing but logarithmic mean temperature difference for the parallel flow. Substituting these values in this equation, we can find out the LMTD. Once if you find out the LMTD, and also you can calculate overall heat transfer coefficient by using this formula, that is U is equal to Q divided by A into delta Tm. So this after that we can find out the effectiveness of the counterflow heat exchanger. This is the formula to calculate counterflow heat exchanger for the effectiveness of the heat exchanger. Okay, these are the conditions. So this is how we are going to calculate the values for various conditions. So here you can observe this along the y-axis the temperature will be there, along the x-axis the distance from the inlet. Okay, as the increase in the length, so you can observe the temperature of the cold hot fluid will be reduces because it is length of the pipe, depends upon length of the pipe. So you can observe the action, counterflow action. The hot fluid is moving in the direction and cold fluid is moving in opposite direction. Okay, this is the temperature difference theta I and theta O. Okay, so here it is taken, it is delta TO, that is also nothing but theta O and theta I. Okay, this will gives the values of LMTD. Okay, you know that theta I minus theta O divided by ln of theta I divided by theta O. This is the equation. So from that we can calculate LMTD and effectiveness and overall heat transfer coefficient. Okay, I hope you understand this concept. Thanks for watching this video. Hello students, welcome to the heat transfer lab. Now we are going to discuss the calculation part of the test on counterflow heat exchanger, that is experiment number 9. So here you can see the diagram. So how the heat is exchanging from cold fluid to hot and hot fluid to cold fluid. So first of all, counterflow heat exchanger means you can observe this diagram. The cold fluid is moving in one direction, the opposite direction the hot fluid is moving. So this is how the nature of heat diagram we can see. So here at the left side the temperature difference is we call it as delta TO, and the right side the temperature difference, that is delta TI. Okay, along the y-axis and x-axis are temperature and distance of the from the inlet respectively. Next, so here from this experiment we are going to calculate first LMTD. There are three things we have to calculate. LMTD, that is the logarithmic mean temperature difference. Second one is that is overall heat transfer coefficient, and third one is the effectiveness. Okay, so let us see what are the observations are there. So here we are going to calculate what is the time taken for cold water and hot water, the time taken for the cold and hot water in the heat exchanger. So first one is the time for 1 liter flow of cold water, that is TC is equal to 95 seconds, and time for 1 liter flow of hot water, that is TH, is 11 seconds. So inlet temperature of the hot water, that is THI, is equal to 46 degrees centigrade, and inlet temperature of the cold water, that is TCI, that is 32 degrees centigrade, and outlet temperature of the hot water is THO, that is 44 degrees centigrade. Outlet temperature of the cold water, the TCO, 38 degree centigrade. So all these four temperatures are there that can be noted down by the help of thermometer at the exit or inlet of the water or fluid. Okay, so we have to note down this corresponding temperatures with the help of thermometers. Okay, next one is we have to do the calculations for the mass flow rate. So there are two mass flow rate, one is hot fluid and cold fluid. To calculate mass flow rate of the hot fluid, so you know that mass flow rate means there is a unit is kg per second. Here 1 kg of water, or you are consider 1 liter. So for this analysis purpose we consider that is 1 kg of water is flowing into the heat exchanger. How many seconds they have taken? It is taken, that is 11 seconds for the hot fluid. So 1 divided by 11 is nothing but 0.09 kg per second. Similarly, if you consider for the cold water, similarly 1 divided by Tc, that is 1 kg divided by 95 seconds, that is 0.111 kg per second. This is the mass flow rate. Okay, next we have to calculate what is the heat transfer for the hot fluid and cold fluid we have to calculate. So we know that from the basic equation, the QH is equal to mH CPH into THI minus THO. So we have to substitute the values 0.09, 4.18 in 10 to the power of minus 10 to the power of 3, that is the specific heat of the water, and 46 minus 47. 46 minus 49. So the QH is 753.66 watts. And temperature, fourth one is QC, that is heat transfer for the cold fluid. Similarly, MC into CPC into TCO minus TCI. So 0.111 into 4.18 into 10 to the power of 3 into 38 minus 32. So you will get 2791.05 watts. This is how QH and QC. The next one is we have to calculate LMTD. To calculate LMTD, we must know what is theta 1 and theta 2. Theta 1 is, we can define, that is THI minus TCO. So THI is temperature of the inlet hot fluid temperature, that is 46, and TCO is temperature of the cold fluid at outlet, that is 38. So you get difference is 8 degrees centigrade. Similarly, for the T2, THO minus TCI is equals to 44 minus 32, you will get 12 degrees centigrade. So substitute this equation in LMTD equation, that is theta 2 minus theta 1 divided by ln of theta 2 divided by theta 1. So that is 12 minus 8 divided by ln of 12 divided by 8. You will get 9.86 degrees centigrade. 9.86 is the LMTD. Okay. Next, we have to calculate overall heat transfer coefficient. To calculate overall heat transfer coefficient, we need area. The area of the pipe, that is pi dl. So we'll get 0.0314 meter square. So substitute all the values, diameter of the pipe and length of the pipe. We know that length of the pipe is 1 meter, and diameter you have to substitute. It is given in the designer specification, that you substitute, and you'll get 0.0314 meter square. Then overall heat transfer coefficient for the hot fluid, that is QH divided by A into delta Tm. So that is 753.66 divided by 0.0314 into 9.86. That is 2434.27 watt per meter square degree centigrade. Similarly, for UC, that is QC divided by A into delta Tm, that is you will get 9015.01 watt per meter square degree centigrade. This is the overall heat transfer coefficient. And finally, the epsilon, that is THI minus THO divided by THI minus TCI. So this is the effectiveness. So effectiveness of the heat exchanger will get 0.1428. Okay. Thanks for watching this video.